So, today we begin with a fable. Far, far away from here, there lies a land called Never 50, where it is illegal to travel at a speed of exactly 50 miles per hour. You can go slower, you can go faster, but not exactly 50. One day in Never 50, Crazy Driver is arrested after it is found that he has traveled exactly 200 miles in 4 hours.
Mr. Driver, you were going average speed of 50 miles per hour, so I find you guilty of driving 50.
See, here's the thing. You can't point to a particular time and say that I was driving 50 at that point in time. You know, maybe I went a little faster sometimes, a little slower than others, but you can't say that it was at one particular point in time I was driving 50. So who's right? To recap from the top, Crazy Driver drove 200 miles in 4 hours, in other words, at an average speed of 50 miles per hour. And the judge says, Mr. Driver, you were going at an average speed of 50 miles per hour, so I find you guilty of driving 50. And Crazy replies, but you can't point at a particular point in time and say that I was driving 50 at that point in time. So who is right? Well, the answer lies in the mean value theorem. So that's our topic for today. Hi, I'm Tim Hsu from San Jose State University, and today I'll be talking about the mean value theorem. I'll talk about the statement of the mean value theorem, and talk about some consequences of the mean value theorem, like what is the point of the mean value theorem. So without further ado, the mean value theorem says that suppose f of x is a function such that f is differentiable on the open interval ab and f is continuous on the closed interval ab. So, details aside, the point is that f is a nice function, much like pretty much every function you've seen in calculus, other than those functions that are specifically identified as being not nice. Anyway, the point is, in that circumstance, there must exist some number c such that strictly between a and b, such that a is less than c is less than b, and f prime of c is equal to f of b minus f of a over b minus a. That's what the mean value theorem says. So what does that mean? What is the significance of this particular formula? Well, in other words, the point is that at that point, at magical point c, the instantaneous rate of change f prime of c, so remember f prime of c is the instantaneous rate of change at c, is equal to the average rate of change. So if you look at the average rate of change over the entire closed interval ab, you get the change in y over the change in x, which is f of b minus f of a over b minus a. And for some c strictly between a and b. So there's some c in there not equal to a and not equal to b, but somewhere in the middle where this equation occurs, where the instantaneous rate of change is equal to the overall average rate of change. Now, the weird part, here's the statement of the mean value theorem. Again, the weird part about the statement of the mean value theorem is the following thing. While there's always going to be some value c, is this point here, this is the weird part. There's always going to be some number c strictly between a and b, where instantaneous rate of change is equal to the average rate of change. You can't predict where that c will be. It could be close to the beginning, could be close to the end, could be somewhere in the middle. You have no idea, based only on the given information, you have no way to predict where that c will occur. So that's strange. I mean, it's a strange thing that you can actually prove that it must happen somewhere in there, but you don't know where. Weird. All right, so here are some other ways of thinking about the mean value theorem in terms of rates of change. So again, assuming f is nice, that is differentiable on the open interval ab and continuous on the closed interval ab. Remember what the mean value theorem says, that there is some c strictly between a and b, such that the instantaneous rate of change at c equals the average rate of change of f on ab. So just going back, so the instantaneous rate of change at c is equal to the average rate of change on the closed interval ab. So if f happens to represent displacement or distance traveled, then interpreting that same statement says that the instantaneous velocity at c, at time c, is equal to the average velocity over the whole interval ab. Now where can we apply that? Anyway, so geometrically, this is also a very popular interpretation. This is also a way that maybe is, if you're sort of visually inclined, this is a good way to remember what the mean value theorem says. So the mean value theorem says that the slope at x equals c, that's the slope of the red line here, is equal to the average slope on AB, the slope of the blue line over here. So in other words, what the mean value theorem says is that there is some point here, in fact there are actually 2 points, there's one point kind of around here and another point over here, where the instantaneous slope is the same as the average slope. So that's what the mean value theorem says. Here, I should also mention one special case of the mean value theorem, which is Rolle's theorem, which says that suppose f is again a nice function differentiable on the open interval, on the inside of the interval, and continuous on the whole entire interval, including the endpoints. But suppose we also require one extra condition, which is that f of a equals f of b. So if you go back to the previous picture, this is the situation where the left-hand endpoint and the right-hand endpoint are at the same height. So in that case, there must we conclude that there exists some number c strictly between a and b. Again, it's in there somewhere, but we don't know where, such that f prime of c is equal to 0. And this is a special case of the mean value theorem precisely because when f of a is equal to f of b, so this is the extra condition that we added to the assumptions of the mean value theorem to get Rolle's theorem. So when f of a is equal to f of b, then remember f prime of c is equal to that average rate of change, f of b minus f of a over b minus a. Well, if f of a is equal to f of b, then this numerator is 0, and so the average rate of change is 0. So this f prime of c is equal to 0 here in this particular case is exactly saying that the instantaneous rate of change is equal to the average rate of change. So I mentioned this, well, you don't really need to know this in the end because it's just a special case of the mean value theorem, but I did want to mention this because the usual way in which you prove the mean value theorem is to start from the extreme value theorem, the fact that says if you have a continuous function on a closed interval, it has a maximum and a minimum in there somewhere, and use that to sort of prove Rolle's theorem. That's the sort of nicest way to go about it. And then an additional algebraic trick then gives the mean value theorem. So, while this is just a special case of the mean value theorem, it's sort of, up to some algebraic trick is basically the same thing. All right, anyway. So that's, just for the proof fans of the audience. All right, so let's talk about some consequences of the mean value theorem, and here it is stated again. There are lots of consequences, but the two in which we'll be most interested in this video are the zero derivative theorem. That's probably the most important consequence of the mean value theorem, and also the fact that having a positive derivative, having f prime of x greater than 0 all throughout some interval I, means that f is going to be an increasing function all throughout that same interval I. If you don't remember what an increasing means, I'll remind you more precisely when we get there. Okay. Oh yes, and you may have seen this idea already, that positive derivative means increasing, or if you haven't, depending on the order in which you cover these topics, you may later see this as part of what I like to call the box. It's the sort of the summation of calculus 1 in a box. All right, so first the zero derivative theorem. So suppose f prime of x is equal to 0 for all x in some interval I, then it follows that f must be constant on that interval. So remember, if you have zero derivative everywhere, then you must be constant. So proof, and in the end, that's what the mean value theorem is good for. It's for proving things, and so we have to utter the p word here. Sorry for sensitive ears. So suppose a and b are points in I, and might as well let a be less than b just for the sake of notation. Then applying the mean value theorem to the closed interval ab, we see that for some c between a and b, again, the average rate of change on AB is equal to the instantaneous rate of change at C. So f of b minus f of a over b minus a is equal to f prime of c, which has got to be equal to 0 because f of prime of x is always equal to 0. That's our original assumption. So if you multiply by both sides by b minus a, we see that f of b minus f of a is equal to 0, or in other words, f of a is equal to f of b. So what did we just show you? Show that if you have any 2 points in the interval, their f values are equal. So since this is true for any 2 points in the interval, f must have to take the same value at every single point of I. In other words, f is constant. That's what it means to be constant. Da, 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 da. All right, so turning to the positive derivative version of that theorem, suppose instead of assuming that f prime of x is always 0, suppose f prime of x is always positive for all x in some interval I, then f is strictly increasing on I, or if you don't remember what that means, let me remind you that to say that f is strictly increasing on the interval I means that if you have 2 points, a comma b in I, and with a less than b, then f of a is less than f of b. That is, increasing x means increasing y. So proof, well, suppose we have 2 points a comma b in I, and a is less than b. Then again, applying the mean value theorem to the closed interval ab, we see that for some c such that a is less than c is less than b, f of b minus f of a over b minus a is equal to f prime of c, and which we said, sort of by assumption, is greater than 0. Remember, we're always assuming that this derivative value is positive. And so we see multiplying multiplying both sides by b minus a, that f of b minus f of a is positive, which means that f of b is greater than f of a. So there we go. Da, 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 da. All right, so that's enough for now. Well, except for one thing. The conclusion of our fable.
Mr. Driver, by the mean value theorem, your speed is some inches was equal to your average speed of 50 miles per hour.
So remember what the mean value theorem says, that there is always some point in time where instantaneous speed is equal to overall average speed. We just can't predict where that time will be.
Guilty as charged, I sentence you 1 banana peel.
1 banana peel? What's that supposed to mean? I'm getting out of here. Wah!